Welcome everybody to Passive House Accelerator Live's 101 Deep Energy Exterior Retrofits. We have Kara Haggerty Wilson from Onion Flats with us today. We are thrilled to talk about existing buildings and why it's so important to get them right. With that, I'm going to hand it off to my co-host, Sean St. Amour.
All right. Well, one thing that Kim put in the chat is yes, we are 30 days away, 1 month away from the amazing Reimagine Buildings Best of Retrofit. So make sure you put that on the calendar. We'll talk about it at the end of the show, but because today is Kara talking about retrofits, this deep energy exterior retrofits. And she joined Onion Flats in 2017 as a registered architect and certified passive house designer. Her expertise in affordable housing, institutional design, and deep retrofits has been central to the firm's evolution from a develop, design, build practice to a high performance architectural consultancy. Today, she leads detailed planning coordination efforts at Onion Flats' most ambitious deep energy retrofit project. I stalked them. They are amazing. And now we're going to hear about it. Kara, over to you.
Awesome. Thank you. And I really, really loved that video. I don't know if I've missed it in the last couple of weeks, but that was awesome. Okay. If everyone can see my screen, we will get going. So this presentation is on deep energy exterior retrofits, and that exterior is a very, very deliberate add there to a typical DER. We're going to be looking at projects that approach all or almost all of the interventions from the exterior side rather than the interior side. And now we're moving. So deep energy exterior retrofits, what are they? They're envelope upgrades plus system upgrades plus renewable energy. And what all that yields is old buildings that perform like new, or depending on where you're building and what code you're building to, they might perform better than new construction. And at the same time, we're going to minimize embodied carbon, we're going to minimize disruption to tenants, and hopefully minimize cost to owners. And then the why. These stats are out there all over the place, but buildings are responsible for about 40% of annual global CO2 emissions. And a lot of institutions, a lot of cities have this 2050 decarb goal. And what's important to know is that 80% of the buildings that will exist in 2050 that are going to get us to that goal have already been built. And so it becomes a reality check pretty quickly that existing buildings matter when it comes to decarbonization. So we are trying to formulate hopefully replicable pathways to deal with getting poor performing older buildings to perform like new or better through our deep energy exterior retrofits. And then really briefly, the work that I'm going to present today is all in Massachusetts, and you all probably have a good handle on what's going on in Massachusetts, but there are some drivers there that are promoting this work specifically. They have progressive building and energy codes adopted throughout the state, where for new construction, at least, you're looking at passive house or equivalent performance standards as base code, more or less, as well as significant alterations. And I'll say a slight caveat here is none of the work or projects we're working on actually approach a level 3 alteration. So they don't trigger the requirement for passive house. We're living in a very low impact code world with these projects. But there are other drivers there. One of them is Boston's BERDO requirements. So there's emission standards and reporting requirements alongside penalties for poor performing buildings. And those standards decrease over time with the end goal, again, in that 2050 year to reach net zero emissions. So there's a real incentive to get your existing buildings to be operationally very efficient. And then for the sticks, the code and the emissions reporting, there's also some carrots. There's the increase of grants and funding opportunities that are specific to carbon reduction goals. So you might have an amount of money per MMBTU projected reduced for your retrofit. And then although our federal programs are phasing out and or incredibly uncertain, there are still, at least in Massachusetts and in other states too, there's innovative state and city-led programs that are still seeking to expand and support these types of projects. So there's still folks out there that are pursuing these projects. And then really, really quickly, I'm going to talk about 2 projects today. I wanted to do a third, but we won't have time. So this grouping here is like an amalgamation of 3 projects, and some folks are on all 3 projects. We've got clients, we've got builders, we've got engineering consultants, code consultants, lenders, funding sources. It takes a really big, robust, smart team to make these things work. Just wanted to acknowledge that. And then without further ado, we'll dive into the first case study, which is the Hano Homes project in Boston. This project was completed just this past spring in May. And I'm going to talk about both projects kind of in the same way, where we talk about envelope and systems renewables. And in the case of Hano Homes, resiliency. And I know resiliency is a big like umbrella word. It can mean a lot. In this specific case, it's going to be dialed into battery backup resiliency. So quite literally resiliency there. But so from the envelope perspective, what we're doing, and is a high level summary for Hano Homes, we're demolishing back to the original sheathing. We're installing a continuous airtight layer, and then we're overcladding with carbon storing wood fiber board insulation. We're limiting the interior work to only what's absolutely necessary to install new systems, and then replacing appliances and fixtures that are at the end of their useful life. So really, really light touch interior scope. For our systems, sorry, my button's not working. There we go. We're going to right size our HVAC systems. That's going to be reflective of the improved envelope conditions with the thermal and air tightness improvements. And then we'll, for the first time ever, give them cooling. These buildings never had cooling except for window units. So they'll have new heat pump technology, heating and cooling, energy recovery units for balanced ventilation, and heat pump hot water heaters for domestic hot water. And in the case of Hano, we're fortunate to be able to install solar. We have a flat roof or a series of flat roofs. So we'll be maximizing our solar footprint and decreasing our grid dependency. And then a very late in the game addition, exploration of battery storage, which we went down the path of FIAS Revive 2024 with this project, which led us to battery storage. There were some inherent challenges there, but still a very worthwhile study for this project. And so all that kind of leads us to taking an 1890s era 20-unit building with an EUI, an existing EUI of about 53 kBtu per square foot year, and transforming it into a healthy, resilient building approaching net zero emissions. So really quickly, for both the projects, there's going to be existing conditions that are challenging, and as well as like client-focused challenges as well. Goals or directives that are challenging, as well as certification goals that these projects are going after. So for Hano, the existing conditions are, we've got 10 attached duplexes. They're constructed in the 1890s, so it's a pretty old building. There's been multiple interior and exterior renovations over time. You can see on the photo on the left, there's 4 or 5 layers of cladding that we uncovered there. So everything they were doing was very additive. They weren't repairing things, they were just kind of adding more. Wood frame construction with brick party walls, 2 stories and a basement, 20 units, about 26,000 gross square feet. The existing systems were gas-fired domestic hot water and hydronic baseboard, and then they had the AC window units. The only ventilation in the building as it existed was kitchen and bathroom exhaust. And there's our estimated baseline EUI of about a 59 kBtu per square foot year. So the challenges here were, it was important to the client that relocation was minimized and that the tenant impact was minimized. These are affordable housing units, and the goal here was that we get everything done on the interior within 2 weeks per site, per duplex. We also have a smaller site and tight clearances. The buildings are just barely set back off the property line on a few faces. There's not a lot of room to work. There's not a lot of room to lay out. So we see that as a challenge. And then what you can kind of see in the photo at the top there again is everything was additive over time. So there was rot repair that's probably been around for decades that needed to finally be addressed. And typically at the lower half of the building is where we saw a lot of that required. Our project goals, we started with FIAS Core 2021. This project is design certified in FIAS Core 2021. We ran into some air tightness challenges in the middle of construction. And so we pivoted to FIAS Revive 2024. And that, if anyone has dove into that yet, that's a totally separate animal. And it was an adventure to dive into that. But ultimately, the project didn't meet the air tightness goals of even FIAS Revive 2024. We are still better than new construction code, but we just couldn't get down to our winter resiliency air tightness requirements. But you'll see at the end when we kind of like overview the results, it's still pretty impressive. So we're still pursuing our Energy Star multifamily, DOE Zero Energy Homes Ready, and EPA Indoor Air Plus. So really quickly, the scope and the impact mentioned before, it was really critical that the interior scope was minimized to reduce the impact to tenants. So we're looking at very selective new appliances, fixtures, casework, and finishes where they've been identified by the owner and property manager and or where they're required to meet VS prerequisites. We're disconnecting a kitchen and bathroom exhaust in preparation of the new ERV, taking that on. And then we're installing select mechanical shafts and soffits to connect the new HVAC equipment to the units themselves. All of that within the span of 2 weeks per building. So you can see we've got our 20 units in 10 kind of groups, right? They're duplex. And we were fortunate enough to be able to have 2 hoteling units on site. So while we're asking folks to relocate, they are just kind of shifting to another unit on site, which doesn't always happen. So this is really, I think, fortunate for this project. And then really quickly, the envelope, what did we do after we got back to kind of the original construction? What did we add and what does it look like? And I guess also first, what were some of the challenges? There's bay windows on this project. They kind of meet and they form this very acute angle. So at the very onset of the project, we thought about panelizing, and this angle and some of these other complexities pushed us away. I also mentioned the tight street access. There's a lot of overhead wires as well on the street face. It was going to make for some interesting possibilities for panelizing. So really gearing this towards a site-built project. And then at the rear and side of the buildings, there's decks and stairs that serve as the second means of egress. So there's basically a lot of things that are plugging into the building, and more pushed us towards a site-built solution. And while we have smaller scale repetitive exterior elements, the building is 130 years old. They're not truly identical. Everything is a little unique in some way, shape, or form. So while it looks like a nice little like cookie cutter stamp, it's not actually in reality. So all those things to say, we were looking at stripping back the building and then building back on site with site work. Starting at the bottom, the basement in every building was basically only conditioned by excess heat from the boiler. So it was kind of unconditioned space. They're not actually accessible to tenants. They're really just for equipment. But we're coming back with an R30 6-inch EPS over the exposed foundation on the street side, on all sides. And then the original floor ceiling assembly between the basement and the first floor already has a flash and bat situation. So we've got about 3.5 of closed cell and 7 inches of fiberglass. So we're not adding anything to that. And we really didn't even open that cavity during the project at all. What we did do is we added a spray applied air barrier onto the face of the exposed ceiling. When we get to the field, the main walls, again, those walls at some point over time had been opened up in spray foam. So we had 4 inches of closed cell spray foam existing in the walls. We're getting back to the original sheathing, installing a layer of zip sheathing, which does a couple of things. It gets us our integral air water barrier, but it also allows us to kind of get to a more planar solution for our cladding, because we were dealing with, you can see in the photo at the bottom here, some really, really old sheathing. And then on top of that, 5.5 inches of wood fiberboard overclad insulation. Up at the roof, we, again, 8 inches of closed cell spray foam existing. And really interesting too, another 4 inches of polyiso on top of the deck, which was great. We left the existing roof membrane in place and we added 2 inches of polyiso over top. So you can see we're getting to some really high R values here with kind of minimal intervention. And some of that is based off of the existing conditions being probably different than what you would expect for a 130-year-old building. And then for the windows, I will say we've got our 2-week relocation plans per dwelling, per building really. But the exterior work more or less was on its own schedule. And so it was important to find a way to allow that to happen without needing to interact with the building interior at the same time. So you'll see we came up with this buck solution that could be fully installed and sealed and allow the exterior overclad to continue even when the new windows were not yet installed. So there's a couple progress shots here of the install, and then you can kind of see at the bottom there where you can see which units have had their interior work completed versus those that have not yet come up on their schedule. And then I mentioned before, we didn't hit our air tightness goals, and it was mostly because of this detail. So we've got our exterior wall assembly air barrier at the face of the zip sheathing. We've got our floor ceiling assembly, which remains more or less concealed during construction. And then we applied our interior ceiling air barrier, which is like a blue coating. And you can see pretty quickly what's missing, right? There's some discontinuity there. So we had a midpoint blower door. We had a couple of them actually, to kind of verify what we were doing and what kind of impact it was having. And it became very clear at that point that we had an air leakage path. And these details are drawn in such a way that everything's in contact, everything's touching, and it's just not reality. You can see in the photo here, what we expected to be a 3-wythe brick wall was actually a 2-wythe wall with a pretty sizable gap in the middle. And so that gap served as a conduit for air leakage through the building. And while we couldn't get to 0.06, our original goal, and we couldn't quite get to 0.16, our revive goal, we were able to get to a 0.26, which is still, like I said, better than code. And you'll see in the results here, it has a tremendous impact still on energy consumption. So really quickly, I'm gonna check my time here on our systems. We have a ventilation routing approach that sees us installing supply and return ductwork from ERVs in the basement to the units themselves, as well as heat pump condensate, which is routed throughout in interior chases, back draining to the basements. And then for the outdoor and exhaust air from the ERVs, as well as the refrigerant lines, we're actually routing them through the exterior overclad insulation. So they're basically poking out through the water table, coming up through a datum line between the water table and above, and then they're just getting away from each other so that we can get our clearances and that we can locate them far enough away from operable windows. So each unit has a slightly different configuration for how that works. And then as far as components, system components in the basement, every building had an electrical service upgrade to a 300 amp service. We are swapping out our old gas-fired hot water heaters with heat pump hot water heaters. Each unit gets their own 100 CFM ERV. And then we've got non-ducted heat pump systems in the dwelling units there. So we have condensers at grade. I think we're really fortunate to be able to have a solar system on this project as well. And the city of Boston we were able to negotiate with them to basically, instead of having 10 roofs, we can consider this 5 roofs. So we get to basically negate that single party wall in the center of the 2, which allows us to not have to consider those required setbacks. And it was a pretty dramatic increase in panel quantity just by that one move. So looking at a 67.6 kilowatt array for the entire site. So this project is complete. We have results that are both measured and still projected. We'll hopefully get more measured results as time goes on, but even without hitting our air tightness mark, we're still looking at a 68% improvement on air tightness from the original tests that we did, the existing tests. Our embodied versus operational carbon payback is 6 months, so we're almost there. And that's almost entirely due to the carbon storing factors of the wood fiber overclad. And then when we start to look at our energy consumption projected reductions, we start with a 59.2 with our envelope and systems, and even with our 0.26 air tightness, we can get down to about 18.25 UI. When we layer on the solar, we can get down to about a 4.89. And then these are some real numbers. So we're fortunate to be able to get numbers from the client and their property management team that are willing to share. We've got some weather normalized historic data from 2018 through 2024 compared to 2025 in the month of June. And if you recall, the last week of June, we had an insane heat wave along the East Coast and probably elsewhere, but certainly in Boston as well. And we are tracking unit to unit, anywhere between a 40 to 70% reduction in energy consumption. And that's without any solar installed. So the solar is not yet even installed on the project. This is just robust air tightness interventions and thermal improvements and system improvements. So it's doing what we hoped to see. And we're going to continue to track this and keep an eye on it. And there's a lovely photograph of the outcome. So I'm going to roll right into the second case study, which is the Salem Fairweather Deep Energy Exterior Retrofit. And the same idea, we're going to talk about envelope systems, renewables, and how we're approaching it for the project. So in this case, we are installing a vapor open continuous airtight coating over an existing brick, and then we're going to have a panelized overclad that includes continuous insulation. This project limits interior work to only what's necessary to install the new systems and to integrate the panelized overclad at the window openings. So incredibly selective interior work. Same as Hano, we're going to right size our HVAC systems. They're going to be reflective of those improved envelope conditions. We'll have new heat pump VRF heating and cooling, energy recovery units on the roof, and heat pump hot water heaters with CO2 refrigerant. And then this project has a funding requirement to be net zero. So you'll see we have a pretty impressive solar array proposed for the roof, which will just further decrease our grid dependency. So all in all, the summary for Fairweather is we're transforming a utilitarian 1960s era building with an EUI of 165 kBTU per square foot year, a real energy hog. We're going to turn it into a hyper resilient building that approaches net zero. This one has a lot of existing conditions and challenges. So I'm going to name as many as I can, but it's constructed in 1967. There are some minor alterations in 2007, including adding this lovely elevator tower you see in the top photo. It's one of 4 Fairweather buildings. They're kind of sister buildings where they're built from the same set of details. So they have different floor plates, but they're built at the same time by the same architect, same contractor. The hope here was that we take the largest one, Salem, we find a solution, and then we can replicate it for the sister buildings. But it's non-combustible construction, steel structural frame, masonry exterior. It's 6 stories plus an elevator penthouse. It is not a high-rise, which is really helpful. There's a partial basement, and the majority of it is slab on grade. 127 units, the majority of which are studios. So this is an intensely repetitive floor plate, which is also really, really helpful for the solution that we've come up with. It's about 74,000 gross square feet. Existing systems include a cogen. We've got gas, hot water, and hydronic baseboard heating, and then through wall AC units that are seasonally removed. There's also an air handler, which is non-functioning, that serves the corridors and common areas. And then the kitchen and bath are direct ducted exhaust to the roof. And as I mentioned, the EUI for this building, the existing EUI is projected at about a 165, and that's assuming the air handler is functional, to meet like code. The real challenges here, and that kind of one of the most important parts of this project, is that there is no tenant relocation planned. We are never going to ask people to move out of their apartments. Again, this is affordable housing, and in this case, it's senior affordable housing. There are also a lot of rooftop tenants on this project. We've got 4 or 5 different cell phone companies that have either equipment on the roof or on the building. You can see a little bit of that in the top photo at the elevator tower. And then another prime importance for this project was that we cannot trigger fire alarm replacement for this project. They have a functioning fire alarm system in this building. However, the cost and scope to replace it is not included here. So everything we do needs to be within those constraints. And then as another layer, there are environmental aspects of this as well. The building is from the 1960s. There are some portions of the finishes that are considered environmentally hot. And so the goal here again is to have the lightest touch possible on the interiors, and environmental was part of that, not to disturb what's there. Our goals here are currently FIAS Core 2021 and or Revive 2021, which are very similar. Energy Star multifamily, DOE zero energy ready homes, EPA indoor air plus. And then I mentioned this project has a funding requirement to be at net zero in some way, shape, or form, whether you do it on-site or off-site. And that is a function of the Green and Resilient Retrofit leading edge funding, which has a large portion of this project is funded through. So our scope and impact as far as tenants, the all important no relocation aspect of this. In each unit, there's kind of chunks of scope that's been delineated as what needs to happen. And the plan is to get each of those little mini scopes done within 1 working day. So someone's in your unit, you go down to the community room, you come back at the end of the day, everything's cleaned and buttoned up. And you may have 5 or 6 of those days over the course of construction. So over the course of a year, you may be asked to go hang out somewhere else for a day, but nothing consecutive, nothing that makes you have to relocate your furniture necessarily, or, alter your day-to-day activities. So in order to do that, a lot of the planning is geared to prioritizing that. So we've got our fan coil units, which will be our new heating and cooling in each of the units. They're going to land in the same place that the current AC units live. So we're not changing or affecting how people can furnish their apartment, for instance. They're going to have an AC unit one day and they come back and it's a fan coil unit in the same place. The electrical service upgrades and the tenant load centers upgrades were prioritized. So those are complete, but those were also phased in such a way that one of those 5 to 6 days basically has already happened. We've already asked people to hang out for a little bit to get their electrical load centers upgraded. We're going to be reusing existing exhaust ducts and shafts, and all of our new supply air ducts will run on the outside of the existing wall, in between the existing brick and the backside of the new panelized overclad. So we've got a 9-inch gap where we're going to be running ducts, as well as line sets and condensate. I just mentioned all the refrigerant and condensate lines run outside. The supply registers are integrated into the window assembly, which is part of the panelized solution as well. So we're not actually having to poke another hole in the wall just to get the fresh air into the unit. It's going to be completely coordinated in the window jamb. And then we're also installing the windows in the panel, obviously, if we're going to panelize this. So everything's kind of arrive on site and be installed. They'll come back on one of those 5 to 6 days will be the day that they take out your unit window and kind of seal up the perimeter. So really quickly, ground floor plan. We've got some fresh air to common area spaces that's being handled maybe more uniquely than what's going on the upper floors, which is very repetitive. The crosshatch zone is where we can actually land equipment outside. We've got some steep slope conditions on this site, so we are limited in some ways. And then we've got our new electrical room, which this work is complete. And our new pad mount transformer, while we hoped it was going to be right outside the room, it's actually kind of down the hill, but that work is complete and we're ready to go. And then just highlighting a few things. We've got existing centralized laundry. The client, POA, they're used to heat pump dryers, so that they're not scared by that. So we're lucky in that we get to swap out what's there with heat pump dryers in a multifamily setting. Planning on a future terrace area. And then there's some additional interior work in the blue hatch, which is completely unrelated to the DER scope. It's more like we're here, let's optimize our office layout a little bit. And then when we get to the upper floor work, this is where the DER scope is living, or the minimal scope is living, I'll say, where we've got fresh air to the corridors is handled by decentralized, basically little mini ERVs at either end. And then the knuckle of the building, we have where our duct shaft currently is. We're going to abandon those ducts in place, seal them up. And then the typical unit work you can see here. So we're replacing our tenant load centers and feeders. That's complete. We've got baseboard heat and a gas-fired boiler that needs to remain functional until the project is entirely complete and we can switch over to the new systems. We can cap those later if needed, but that's not necessary. Very, very select kitchen work. And this is really related to finding anomalies like a cabinet physically installed over an exhaust grill. So things like that are being addressed, but otherwise there is no real kitchen or bath upgrades. And then we're going to infill the transfer grills from the former air handling unit so that there's no free communication of air between the corridors and the units themselves. And then you can see here, we're going to reuse our kitchen and bath exhaust ducts and shafts. So they will remain unchanged, except for new dampers, new grills, and the ducts themselves will be aero sealed. And there's an entire code approach to all of this. And we're being very, very specific as to what we touch and what we don't touch. And because things can really spiral once you start digging into these older buildings. So the goal here is light touch in every sense of the word. And then our new fan coil unit will be located below each window, as I mentioned, kind of in the same location as the former AC units. And the supply register will be in the jamb. And I'm going to try to speed up. So our roof here, we've got existing roof access stair in the knuckle of the building. There's our penthouse for the elevator, and then 2 sets of dunnage, one of which is expanding on existing, and the other is new. We'll land our energy recovery units and some of their heat pumps for tempering. And then we're going to relocate antennas. We're going to optimize them, and you'll see we're adding a bunch of solar, and all of this dunnage requires steel, and you'll see when we get towards the solar end, we basically decided to just build up. And so adding the dunnage for the solar actually helps the antenna folks. They get to kind of optimize their antenna locations as well. And then the blue ductwork in the plan is the new supply ducts. So they are routed and grouped together in vertical drops. They're gonna drop between the existing brick and the backside of the new panel to get to every single unit. So you can see those grouped together. And then the red represents the exhaust ductwork, which needs to plug into those roof locations where the kitchen and bath exhaust penetrate. So I'm going to split out envelope and systems for this project, but it's really impossible to do so. They're incredibly married because of the panelized overcloud approach and because of the ducting in the gap approach. But really, really quickly, we've got our air control layers and our thermal control layers. So we've got a primary air barrier on the in a vapor open fluid applied coating on the existing masonry. You'll see it in some of the photos. It's the blue coating. And then on the back side of the panelized structural insulated sheathing is our secondary air barrier. And so of course we now need to tie these 2 together at top, bottom, and all perimeters. We're gonna thinking about how to keep the building watertight while we're doing this. We're leaving our roof edge flashing intact, and we're going to seal over it and kind of encapsulate it. And just really quickly note that the roof work for this project happened a few years ago. So it's got a brand new roof. It's got insulation that was kind of like maybe phase 1 of this that's complete. And so you see we need to tie those 2 primary and secondary air barriers at the top of the wall as well. Thermally, we are landing this panelized overcloud on a concrete stem wall. We're going to have R10 exterior insulation at that stem wall, and then we have a skirt detail, which is kind of cut off here. Up into the panel itself, we're looking at a structurally insulated sheathing of about R21 with a light gauge metal framing backup and 14 inches of mineral wool cavity bat in that framing cavity. And then wherever we can, we're using that same structurally insulated sheathing to kind of encapsulate and top off the building. And then when we have parapets where our ducts dive down, we're just going to fill that cavity with mineral wool insulation. We've got a panelizer on board, and a lot of the coordination has to do with how these things attach to the building. The current plan is to have a nested channel bracket assembly. It'll be anchored to the existing masonry. It has a connector arm that attaches to the top of the panel, so they're kind of hung. And what that means for us there is that we kind of have the opportunity to pinpoint those connections and coordinate them with all of our duct drops, which becomes hypercritical in getting just right. So right onto our systems here. For ventilation, we've got roof-mounted ERUs with heat pumps for tempering, which are those guys. And we're going to reuse our existing vertical duct shafts through the buildings and AeroSeal, as we mentioned. For heating and cooling, we've got air source heat pumps with fan coils, and the terminal units in each apartment are the fan coils. And then we've got both roof and ground mount heat pumps depending on line set lengths. So the routing, the ducts are elevated above the roof about 2 feet. And that's really to avoid clashes with existing antenna infrastructure, conduit, the existing dunnage as well. And then they are insulated, the ducts will be insulated externally when they're on the roof. When they run into the parapet, they're going to transition to an internally lined. And that was really a decision related to our NFPA 285 compliance. Was we needed to limit any and all exposed insulation within the cavity, unless it was already non-combustible. So that was a challenge, but we've arrived at that kind of transition as a meaningful way to do that. The vertical duct drops, you can kind of see in the diagram here, are carefully coordinated with panel attachment locations, and they want to align and get you to the fixed sash of every window, which presented its own set of challenges. And really important here is that each set of duct drops only serves 2 floors at a time. Otherwise, we would be triggering the need to install smoke dampers. Smoke dampers Our fire alarm system cannot handle those. It doesn't have the capacity for them. And you'd also have some access requirements that we wouldn't be able to accommodate with this solution. So it became very, very important to kind of fine tune the design around that. So here, and there's kind of the all layers on view of systems pre-overclad panel. And so here really quickly to summarize, here's this really neat and tidy vertical duct drop here where we've got everybody's just serving 2 floors only. Supplies going to the fixed portion of the window. In this case, the grayed out area is a fixed glazing panel. And then we're having to be very specific about where the vertical duct drops are in coordination with panel edges and panel attachment. So you can see going through the wall section here, here's our duct transitioning from externally insulated to internally lined, passing through our air barrier, which in this case is more or less the plane of the existing roof. We've got a 9-inch gap. Its airspace has a minimum temperature of about 50 degrees. We're going to have to fire stop everything that goes through this 2-hour masonry wall. So it's another challenge. And then we've got at the bottom of every panel, we're leaving off about 16 inches of sheathing to be installed on site so that all of our line sets, our condensate and drainage can come out of the panel and be organized before we go ahead and sheath it and finish it off. And so we've done a lot of mock-ups. I'll say the unit installed in this top left photo is not actually it's the correct unit, it's just not the correct location. But so we basically have been kind of chipping away at mock-ups here to make sure we've got everything just right. I mentioned this is a code conundrum. There's a lot of really interesting things going on here that we could talk about for a long time, but the gist of it is we've got a 2-hour fire barrier is necessary between the brick and the new panel. It's essentially acting like a curtain wall, right? So every opening we have, every window, anything that penetrates both layers, our existing and our new, we need to have a 2-hour fire barrier there. And so we're doing that with a product called Side Rise, which lives its regular life in a curtain wall fire stopping application. So through a series of EJs and code evaluations, we've gotten the green light to use it in this capacity. You'll see we've got our fresh air register is kind of located high in the window jamb. And then we've got a damper, just a fire damper, as well as having to coordinate that with window shades and whatnot. There we go. And then, of course, our air barrier connection. There's a mock-up of just this part too, of how do we actually do this connection? How do we successfully execute that with all these parts and pieces? And how do we do it in a timely fashion? Because we've only got 1 day to do it per dwelling unit. So I mentioned this project has a really robust solar system proposed. So we started off with, there's a site array right now that'll be upgraded. It's relatively old at this point. We're building on top of the dunnage we already have for other reasons and just elevating everything to have a full array. We're going to get over top all the equipment. We'll get over top the antennas and have no obstructions or issues interference wise. And we'll get a really large array out of it. So in total, site and roof looking about 220 kW. And so that's kind of what that's going to look like. So the results for this project are all projected. We're still shooting for FIAS 2021. So we're still looking at a 0.06 air tightness goal, which would be incredible. If we could hit that, it would be about an 86% improvement on air tightness. We're looking in a range of about 16 months for embodied versus operational carbon paybacks. And you can see we've got a really, really bad, poor performing building at 162 or 165 EUI. If through our envelope and systems, we can get that down to a 24, and then we can further reduce that to a 12.9 with solar. We're looking at a basically 85% pre-solar reduction in energy consumption, which would be fantastic for this project. And I think I'm right on time.
Kara, amazing. I have a million questions. Obviously,
Oh, no.
we will never get to them all, but so good, so good. We have a lot of great questions in the chat as well, but first we're going to just take a quick break and share some events and sponsors. And then we're going to hang out with the accelerator community and go through the questions. Thank you so much.
Awesome. Thank you, Kara. Thank you, Shannon. Let me just get myself situated here. Our podcast episode, if you can't get enough, it's with Kara. So if you'd like to learn a little bit more about how Onion Flats has scaled their deep energy retrofits across their projects, some of the solutions and technical breakthroughs they've discovered along the way, this is the episode for you. There's a link in chat to check it out. Next up, we have a component spotlight event next Thursday. This is with Rockwool. Wildland urban interface fires in Canada and the US and applicable solutions. Just remember, you do have to register for this one, so make sure you do so. Link is in chat for you. Next up, we have a few community events, starting with a fun one. This is BS and Beer Renovations, West Coast versus East Coast. This will be with Rachel White and Josh Salinger online tomorrow, so be sure to check that out. Also, the International Passive House Open Days are taking place this weekend globally. And an event I'm very excited about, Reimagine Buildings Best of Retrofit, is taking place. Kara will actually be a part of our panel in hour 3. This is taking place online December 5th. And we will be speaking with and celebrating the projects, people, and ideas transforming existing buildings for all into healthy, comfortable, climate-friendly spaces. So we hope to see you there. I'll have AIA, THEIS, and PHI credits available for those of you in that kind of last-minute rush to get your credits for the year. 4 hours. There's a link in chat if you'd like to check out a little bit more about the sessions. And over to a few Reimagine Buildings Collective events. We have Kara joining us this Friday. So if we don't get to your answer or you'd like to do a little bit more of a deep dive with her, we have an hour set aside for you. This will be noon on Friday, the Reimagine Buildings Collective. And then next Tuesday, we have a session with Nikita Reed. She'll be speaking with Michael Ingui in a fireside chat, as well as a few other events. I'm going to jump into sponsor thank yous really quickly. And then we can get to Q&A. First off, I'd like to thank our founding sponsors, 475 High Performance Building Supply, Ingui Architecture, Partel, Rockwool, and Zola Windows and Doors. Our champion sponsors are Buiso, Cascadia Windows and Doors, European Architectural Supply, Facro, Intelligent Membranes, Icon Windows and Doors, LG, and Source 2050. Over to our patron sponsors, Building Type, Brennan, Insulation and Air Tightness, Holzraum System, Innotech Windows and Doors, Lamelux, RDH Building Science, and Sanderson Design. And finally, our stakeholder partner is NYSERDA. So thank you, everybody. I'm going to put the Q in the list for us, and we'll get started. Over to Sean.
All right. Well, again, amazing events. So hopefully you put those down and pinned a few of them. And of course, thank you very much to our sponsors. So a lot of questions. We got about 11 minutes, so let's do our best to continue on. And then if you miss it, well, you'll have to continue on Friday. So Chris, you get to kick things off.
Hello, thanks for that wonderful presentation. Couple of great solar arrays. I'm wondering if you're doing anything for snow management. And in the first project, you were considering batteries, and I'm wondering if that program called Connected Solutions, where you sell electricity from the batteries, informed your decision there.
Yeah, I don't think we have any snow management on the solar design for either projects that I'm aware of. I feel like it came up on Salem and it was deemed not necessary, but it's a good question. For the battery backup at Hano, the reason we landed where we landed was we were following FIAS Revive 2024, which helps you size your battery based off of your expected needs during extreme weather events, right? So you look at your worst case in winter, your worst case in summer, and you look at what you need to power to make the building livable, right? So in the summer instance for Hano was when our battery was really becoming pretty big. We needed to not only keep the ERV running at a very low CFM because we now got a pretty tight building, right? We need that ERV running and refrigerators, but also we needed our heat pumps to be powered as well because our cooling was such that unless we had minimal cooling during those resiliency outages, we wouldn't have habitable buildings still. So as we got to the size of the battery, we started to see it wasn't just the equivalent of like 1 Tesla Powerwall. It was the equivalent of 3 per building. And where do you put those safely in a really, really old building that's not sprinklered? So there were a whole host of things that started to come out of that, where we went all the way down the path. We studied it. We looked at it. I think we even started getting pricing for it. But there were some real code considerations that made us kind of pull back and rethink what we were doing in that respect.
Thanks.
Great stuff. Okay, so I got one here now and I'm going to go with when it came to upgrading the electrical panels, you went up to a 300 amp service, and I'm just wondering, did you guys consider some of the smart panels? Because I'm assuming you start off at 60 or 100 amps and then went to 300, and just wondering if a smart panel or even smart breakers were considered before you upgraded.
I don't think they were, and they were I think they were 200 amps to start.
Okay.
I don't think there was any discussion about anything other than we need 300.
Fair enough. All right, moving along. Evan's up.
Thank you.
Evan, perfect.
Oh, sorry. It's Grulich, so it's easier than I said. The last name. Kara, thank you for a great presentation. I can do both of mine. They're just quick questions. You had a structural insulated sheathing. I'm just curious what product that was, because the only one I've sort of discovered is DuPont Armor Wall, and it'd be great to have more than one option.
Yeah. So that one's interesting because we had a product we were using, and I should also say Salem Fairweather is technically on hold, right? Because there's some funding related issues based on current events. How about that? And so before it was on hold, we had a product that we were considering, and we pivoted at the last minute. So there is a competitor to Armor Wall called Rock On that you may have heard of. So we were considering them heavily, and then changed direction at the last minute there.
Okay, thank you. Appreciate it.
Great stuff. Next, Shannon, over to you.
Thanks, Sean. I lost track of my question. Can you help me?
There's a bunch. It's funny. I had to pick
Oh, I
one
thought
between
you
just-
wanted me to ask my question.
Yeah, you've got your question.
I do have my question. All right. Sorry about that. As a
Oh,
delay.
it's all good. There's lots.
Kara, can you describe the non-ducted heat pump distribution strategy for the second project, please? The Salem.
Oh, so it's a VRF. So there's condensers at grade or on the roof, depending on the line set length, and then everybody has a fan coil in their unit, so they can control their temperature. So it's pretty standard stuff.
Yeah, very straightforward. And so
Yep.
if they each have one, they're all efficiency units, right? So there's no challenge there with reaching all the rooms. Okay, great. Thank you. All right, and who is up next? We have.
We're gonna go
this
back
is a
to
challenge to say this name. Risharaj Mathur am I saying your name right? And would you like to unmute and ask your question?
Hi, no, appreciate that. Thank you so much, Shannon. So my question was, and you can call me Raj if that's easier.
Thank
So
you,
my
Raj.
question was, uh, knowing how much investment you put into these buildings, is there any calculation on how much time it'll take to break even? That was the first one. And the second one was going to be which HVAC unit did you guys end up using for the dwelling units in the second project? I was just curious to know. Thank you.
Yeah, I guess right now what's currently planned for the HVAC units it's a Mitsubishi product. Because we're still starting back up, basically we're in like a slow startup period again here. It still could be open, but that's what's planned. As far as like a payback period, I think that's tough to think about when it's affordable housing and the kind of funding streams are varied and layered. And I don't know that that's necessarily even a projection you can make directly. I think it's something to consider for sure, but I don't know that it's something that the client has shared with us at this point.
Thank you.
Mhm.
All right, thank you. And Evan, I know that we gave you a chance to ask questions. We're gonna go to Evan Smith and then we'll keep going because I know we've only got 4
Yep.
minutes. So
Yeah,
Evan
I
Smith,
said
you got
I'm
your
all
hand.
good. I'm
Perfect.
done.
All
Yeah.
right.
Thank you.
Good stuff. All right, Evan Smith, you got your hand up. It is your turn.
Yeah, probably trying to ask the same question, but a little more directly. Do you know what the envelope costs on a square foot basis or a building basis for panel homes? Given that seems like the biggest barrier to retrofits more broadly is actually cost.
Yeah, and we do have some presentations where we do dive into cost and we really start to compare them. I don't have that offhand. I'd have to kind of dig it up, but it is something where we are tracking pretty specifically because we want to understand how these things really pencil in that way. So maybe on Friday I can have that information ready.
Thank you.
Yeah.
Excellent. And next over to Noah.
Yeah, hey, Kara, great presentation. My question was similar to Raj, just around paybacks. So that makes sense. And yeah, if the client hasn't shared that, then, and yeah, I know the capital stack and everything can be complicated. So thank you.
Yeah.
Perfect. And Scott Kennedy.
Hi, we've done a bunch of projects where we've in the past done HRVs for corridor heat recovery, but we're now getting a lot of pushback wanting to pressurize the corridors from the engineers. I was just curious as to what your strategy was there with those ERVs in the ends of the corridors.
Yeah, our strategy was entirely focused on we can't have smoke dampers. It was one of those things that we had two options. It was either what we've landed on or like a PTAC, which would be very inefficient. And so we started with a PTAC and we moved towards let's get these kind of individual ERVs at opposite ends and let's not make any penetrations or anything like that would trigger additional smoke burns.
So they don't pressurize the corridor in any way. And what do? Just supply one end of the corridor and exhaust the other end of the corridor? How do they work?
They're both, each end is supplying and exhausting. So it's not like one is exhaust only and one is supply only. They're both a balanced ERV on either end.
But are they supplying exhausting into the suites, or are they supplying exhausting
No,
in the corridor itself?
Sorry,
the corridor.
just the corridors only. Yep.
Okay, so there's no pressurization of the corridor. It's actually just ventilation of the corridor.
Yes, it's strictly ventilation. Yep.
Okay, thanks.
Great question. Well, that gets us close to top hour. I know we've got questions, but we got to wrap things up. So, Kara, amazing presentation. If you've got more questions, you're now going to have to ask them on Friday because that kind of concludes the 101 on deep energy retrofits. And those two examples that you gave, fantastic. And that being said, we are a month away from the Reimagine Buildings retrofit event. So lots to look forward to. And I mean, I'm watching these projects so they keep going. So it's great to see where they're at and looking for more retrofits as we make our existing buildings a lot better and more comfortable and hyper resilient. That's the takeaway phrase today, folks.
Absolutely. Thank you, Kara. Thanks for joining us. Amazing presentation. Great slides. You got a lot of compliments from everyone in the chat. And we will see you on Friday. Everybody join us for Ask Me Anything with Kara on Friday.
Great. Thank you all.